quick review, investigating the following related to rational functions, right? So we're analyzing rational functions. This is what we went through Friday. We're going to investigate points of discontinuity of the rational functions. And we are going to look at filling in holes of functions, vertical asymptotes, finding the intercepts, both x-intercepts and y-intercepts, finding horizontal asymptotes, finding the domain and range. We're going to be mostly focusing on domain of these rational functions, and then we're going to be using all of this information to sketch the graphs. And in the discontinuities of rational functions, we said that there's two types of discontinuities. Both types of discontinuities are always values that make the denominator equal to 0. So rational functions, the only domain question is, does it make the denominator 0? If it makes the denominator and the numerator equal to 0, right? We said if it makes denominator and numerator equal to 0, it's a hole in the graph, also called a removable discontinuity. So we discussed that on Friday. And then we said if it only makes the denominator equal to 0, the point of discontinuity is a vertical asymptote, and we further defined that to say it was called an infinite discontinuity. All right, so that kind of catches us up to what we discussed in infinite discontinuity, not continuity. All right, so it's an infinite discontinuity, vertical asymptote. And we looked at the graph of one that had vertical asymptotes. We looked at the graph of one that had holes. All right, so we're going to kind of pick up today and move on to the next topic of discussion, which is finding the intercepts of our rational functions. Now, by intercepts, we mean the x-intercepts and the y-intercepts, right, or y-intercept. Because it's a function, it can't have more than one y-intercept. That wouldn't be a function if it did. But finding the x-intercepts and the y-intercept. How do you find the y-intercept for any function?
Make x 0.
Substitute 0 for x. So to find the y-intercept, you substitute 0 for x. Now that's a problem with some of these rational functions. Actually, one of the examples we'll look at the end, you can't substitute 0 for x. Sometimes x equals 0 is a hole. Sometimes x equals 0 is a vertical asymptote, and we can't substitute 0. So to find the y-intercept, you substitute 0 for x if you can substitute 0 for x. Not all of these functions will have y-intercepts, okay? But when they do, it's really, really quite easy to find. If we went back and looked at the simple example we looked at on Friday of a rational function, f of x equals x squared minus 4 over x plus 2, if we plug 0 in for x, what do we get? The y-intercept is x is 0, y is negative 2. So that gives us a point on the graph that we'll be able to make a substitution. So you just substitute 0 for x, and we're left with negative 4 over 2, which gives us negative 2. So that's how you would find the y-intercept, to substitute 0 for x if you can. Now, if we went back and looked at this same function, right, how do you find the x-intercepts? The x-intercepts occur where y equals 0, right? But that's a little bit more complicated than just plugging 0 in for y. So somebody tell me, without writing any of this down, when can that expression equal to 0? When can it equal 0? Only if the what is equal to 0? The numerator, right? Can we get zeros from denominator being 0? No. So a fraction or rational function, the x-intercepts of a rational function, are all values that make the denominator equal to 0. Let's see, I'm going to put this in here. Only the denominator equal to 0. Only the numerator, rather. Why do we need it to only make the numerator 0? Because if it makes the denominator and the numerator equal to 0, it's not an intercept, it's a hole in the graph, right? It's not in the domain. So x-intercepts would be values that make only the numerator equal to 0. So f of x equals x squared plus 4 over x, not plus 4, minus 4. Same function we've been working with, over x plus 2 has an x-intercept only at values that only make the numerator equal to 0. So the numerator is equal to 0 at plus or minus 2, but negative 2 makes both of them equal to 0. So what does this rational function have? Where is its x-intercept? The x-intercept is at 2, 0. 2 is the only value that makes only the numerator equal to 0. We can't use negative 2. There's a hole at negative 2. Okay? So x-intercepts are values that make only the numerator equal to 0. It's pretty easy to find that. Now, as you can see in these little examples, what skill are we going to be using a lot when we're dealing with rational functions? Factoring, that's right. We've got to find the zeros of the numerator because that's the x-intercepts. We have to find the zeros of the denominator because that's the points of discontinuity, values that make the denominator equal to 0, values that make the numerator equal to 0. If it makes both numerator and denominator equal to 0, it's a hole. All right, so finding these zeros is going to involve a lot of factoring. Okay, horizontal asymptotes. We defined vertical asymptotes on Friday as being a domain problem, right? A vertical asymptote is a value that makes the denominator equal to 0. That's bad. We can't have a denominator value that's equal to 0. So that's a vertical asymptote. It's a vertical barrier line. The function can't cross it. Can't cross it. Okay? Horizontal asymptotes are a little different. You can cross horizontal asymptotes. Here's the rules that we'll use to find them, and then we'll talk a little bit more about what a horizontal asymptote is as we continue. In a rational function, if the degree of the denominator is greater than the degree of the numerator, the function has y equals 0 as its horizontal asymptote. Now, y equals 0 is the what? What is y equals 0? Is that the x-axis? Kind of important to know. An example of this would be something like f of x equals, let's just reverse the one that we're working with, x plus 2 over x squared minus 4. Now, does everyone see that the degree of the bottom is greater than the degree of the top? That means the bottom is going to be outgrowing the top. Right? Significantly, if x is 1,000,000, then the numerator is 1,000,002. The denominator is 1,000,000 squared minus 4. So it's much bigger than the numerator. And the bigger x gets, the larger the disparity between the numerator and denominator is. And so this thing is going to 0 as x gets big. As x goes to infinity, this thing right here goes to 0. Right? And that's what we mean by horizontal asymptote. The horizontal asymptote, you guys listen to me, the horizontal asymptote or oblique asymptote we'll look at in just a moment is going to define what the function is when x is really, really big. So as x gets infinitely large, this function is reduced to 0. That's what the horizontal asymptote is. I wish, if we had a calculator that would do lots and lots and lots of decimal places, if you put 10 million in for x, what's 10 million? 10 times 10 to the 6th. 1 times 10 to the 7th, if we really wanted to be in scientific notation. Okay? If you could put that in there, then the bottom is going to be 10 to the 14th. Okay? The top is 10 to the 7th. There's a big difference in those two values. Right? 10 to the 14th, 10 to the 7th over 10 to the 14th is 1 over 10 to the 7th. That's a really small number. It's 1/10,000,000th. Okay? So as x gets large, the function value is getting really, really, really small. It's actually limiting itself to y equals 0. Yes, Ian?
So as long as the zero bottom is bigger than one top, y will always be y equals 0 to the horizontal asymptote.
That's exactly right, regardless. Now, this could extend to non-polynomial functions or non-polynomial rational functions. We could have something like, and this is off your notes. So, but you could have, and you'll look at this when you get into calculus. You could have a function like this, like the sine of x over x squared. So what happens to this one? This one has a horizontal asymptote, but it's 0. But it's 0 for the same reason that the previous one was equal to 0. X squared really grows faster than sine of x. As a matter of fact, we know, we'll learn pretty soon in trig, sine of x just bounces between -1 and +1. It's always taking on really small values. X squared is blowing up. Okay? Even if x was 10,000, that sine of 10,000 radians or degrees, whatever we're dealing with here, radians, is between 0 and 1, -1 and 1 rather. But 10,000 squared is a huge number. So it's some small number over something big, big, big. So if you have something that's really small or slow growing over something that is huge and fast growing, small number over a huge number is close to 0. 2 over 10,000. That's close to 0, right? And the larger x gets, the bigger it grows. And then you'll look at some point, a hierarchy of functions into the end, FEPL. This, again, we're off the notes here, but this is strong to weak growth-wise. It's the hierarchy of functions. N to the n, or x to the x power, is the fastest growing. Factorial functions are next. Exponential functions, polynomial functions, logarithms, and other, like trig functions and things there as well, kind of sine and cosine at least. Okay, that's a hierarchy of functions that you can use to determine if the numerator is outgrowing the denominator. But anytime the denominator is outgrowing the numerator, your function is going to eventually get sucked down to 0. All right? And that's the way it works with polynomial functions. Okay. The next case, and this is a lot of words. If the degrees are equal, the function has y equals a over b as its horizontal asymptote, and we're going to define a and b. It's not actually supposed to be there, just the letter b, not the word b. Horizontal asymptotes where a and b are the coefficients of the highest degree term in the numerator and denominator, respectively. Okay? Let me give you a second to write that down. So the first case says the denominator is outgrowing the numerator. If the denominator is outgrowing the numerator, then the horizontal asymptote is 0. If the degrees are the same, then relatively speaking, they're growing at the same rate. Right? We know that the highest degree controls the shape of the graph. We've discussed that. The highest degree determines everything, how many zeros it has, what the graph looks like, whether it's oriented up or down. That highest degree coefficient rules the roost. So if the degrees of the numerator and denominator are the same, then we can say, relatively speaking, they're growing at the same rate. So we're not going to 0. The numerator and denominator aren't going to win out over each other. They're basically have the same characteristics regardless of what they are. So let's look at an example. If we had f of x equals, let's do 6x cubed plus 5x minus or plus 2 over 3. No, let's don't do 3. That's too easy. Let's do 5x cubed minus 17. This is a case where the degree of the numerator and the degree of the denominator are the same, right? So my horizontal asymptote is going to be y equals what? 6 over 5. Now, what does that mean? What does the horizontal asymptote tell us? It tells us that this very, exciting, somewhat complicated rational function, as x gets really, really big, just becomes 6 over 5. When x is large, it's 6/5. I could guarantee you if we had a calculator that would do it, if x was 10 to the 7th, what we're looking at here is really, really close to 6/5. Has a value of 6/5 as x gets bigger. And the bigger x is, the closer it gets to 6/5. All right? That's what a horizontal asymptote is. It's the limit as x approaches infinity of the function, plus or minus infinity. All right? So you could, in functions, have two different limits or two different horizontal asymptotes if it takes on a different value toward negative infinity. In this case, it wouldn't. Polynomial functions, it wouldn't. Okay? Does that make sense? Do you understand what a horizontal asymptote is? As x gets large, that horizontal asymptote is like a magnet. The function is just going to eventually just get drawn infinitesimally close to whatever the horizontal asymptote is. And that's true if it's y equals 0, if it's y equals number. It's true if it is what we call oblique asymptote, which is not horizontal. All right. If the degree of the numerator is higher than the degree of the denominator, there will be an oblique asymptote. I know we got a lot of notes. We're going to use all these notes in the problems that we're going to work in just a few, today and tomorrow. The degree of the numerator is higher than the degree of the denominator. There will be an oblique asymptote that's not vertical or horizontal. There's one more sentence to this definition. I'm going to write it. Okay. Yeah, it's a slant asymptote. No, not necessarily a line. It could also be a parabola. Yeah, right? It is weird. Okay? Y'all with me? Yes?
Find it, but what does it look like? It's the y. Like is it
All right, I'm going to tell you, you do know how to find it?
Yeah.
How do you find it?
So like if it's y equals 0, it just means that the denominator.
Okay, now we're back to specifically the third case. How do you find the oblique asymptote? Because that's what you don't know how to find that one yet, right?
Right.
Okay, let's go. Is that what you were asking?
Yeah.
Okay. All right. So here's what it is. To find the oblique asymptote, here's just the next sentence in that same definition. To find the oblique asymptote, perform polynomial division. Okay? You perform polynomial division. Now, we could take something like, y'all with me? F of x equals Just a very simple one. X cubed over x. Is that a rational function? It's polynomial over polynomial, right? It's almost everywhere the same as what? It's not a trick question. What is this equal to? Except for when x equals 0. It has a whole. This is x squared, except we have a whole at 0. Right? Now, if I take this thing and I change it just a little bit, if we just take g of x is x cubed minus 8, and x is, the denominator is no longer x, now it's x minus 2. Let's make it x plus 2. I haven't really, if x is really, really large, is there any difference between these two functions? If x was 1 million, then the numerator is 10 to the 12th minus 8. And the bottom is 10 to the 6th plus 2. Really, if x was 10 to the 6th, 10 to the 6th would be 10 to the 18th on the top plus 8. And 10 to the 6th plus 2. Is that a minus 8? Does that minus 8 and plus 2 really have any major effect on things? Relatively speaking, this is equal to what? 10 to the 12th. Plus or minus a few. Okay. Now, does that plus or minus a few really make a difference? Not when x is that big. If I told you I'm going to give you 10 to the 12th dollars, but you gotta let me keep 8. Are you going to feel it? No. Not even a little bit. Okay? You're not going to say, oh, I'm not going to take 10 to the $6 unless you give me 2 more. It's not going to make a difference. It's insignificant, right? So as things get larger, this particular function, is going to adhere to, this is still going to just be essentially x squared as the function gets larger. Now, when x is small, x squared minus x cubed minus 8 over x plus 2 is not going to look like x squared. It's going to have some wrinkles and it'll look different in the middle. It's got a hole at -2. Actually, it's got a vertical asymptote at -2. Wish we had time to look at the graph of this, but we don't. As x gets large, it's x squared. Because x cubed divided by x is x squared. If we wanted to know the exact parabola that's there, we could do. But in this particular case, because there's no linear terms, it would actually be x squared. And we'll look at one that has an oblique asymptote when we do our examples. Okay? So asymptotes don't have to be linear. Most of the time they will be. I'm not going to give you any that have a quadratic asymptote. But the asymptote is just defining, horizontal or oblique asymptote defines what the function resembles most closely as x gets arbitrarily large. All right? Now, let's talk about domain. Finding the domain. Domain is what x can be, right? So in a rational function, the domain is all real numbers except the values or numbers that make the denominator equal to 0. Now we're not going to have an or here. We're not going to consider the other functions at this point. Okay? There's just a period there. The domain of a rational function is all real numbers except the numbers that make the denominator equal to 0. X can be anything unless it breaks the function. How do you break a rational function? 0 value in the denominator. Okay, so if we looked at an example like f of x equals, what have we've been working with? X squared minus 4 over x plus 2. The domain of f excuse me, is everything except for what? Yeah. All right. Now, if I were writing that in interval notation, that's everything from negative infinity to negative 2. We're going to skip negative 2. There's a hole at negative 2, but we'll pick it back up and take it all the way to positive infinity. So that's the domain. That's the interval. That's everything except for negative 2. That's how you'd write it in interval notation. All real numbers except for x. Yes, equals negative 2.
Do brackets, or is it always parentheses?
Yeah, because brackets aren't going to be an issue of domain, because what are we doing with domain? We wouldn't use brackets with domain, because unless they just, in calculus, you could have closed intervals where it could go from negative 2 to 2 and be including negative 2 and 2, and then you would use brackets. But for domain, remember, we're always throwing things away. So domain would have open circles, and infinities always get parentheses. Okay, that's a good question. Now we want to skip this. The other domain considerations, anything that gives you a negative value under a radical also has to be thrown away from functions. Anything that gives you a 0 or a negative value within a logarithm, the argument of a logarithm can't be 0 or negative. I don't really care about you knowing these things or writing these things now. If you're curious and want to know, you can write these things down. That's it. For calculus, that's all the domain issues that you would deal with. Can't have a negative value under a radical, 0 in a denominator, 0 or a negative number within a logarithm function. The argument of a logarithm can't be 0 or negative. Okay? All right, so that's domain and range. Y'all ready? Or domain. Sketching the graphs of rational functions. Here's the process that we're going to take. We're going to sketch the vertical and horizontal asymptotes. You might put and oblique or oblique. You know, we might have an oblique asymptote that we'll look at just a bit. So we'll always let those vertical and horizontal asymptotes use dotted lines because they're not part of the graph. They are going to help us shape the graph. And if you'll remember back to Algebra 2 or Advanced Math, the function will always hug the asymptotes. Always. All right? So sketch the vertical and horizontal asymptotes. Use dotted lines to do that. Plot the points of any intercepts. If we find x-intercepts and y-intercepts, we're going to use those points. That's going to tell us where the graph is within the sections created by the asymptotes. And we're also going to, at that point, we're going to plug x values into the function to find enough points in each section of the function to sketch the graph. Now we'll define what that in each section of the function means in just a moment. The sections are formed by the asymptotes, right? The asymptotes are going to give us these sections, and those sections are going to have the graph in it, right? So we've got formed by the asymptotes. The asymptotes will form sections, and this is going to make a whole lot more sense in a second when we look at our example. Okay, any questions on these before we look at our first example? Any questions about any of the facts that we've discussed so far? We're going to use these notes and facts really closely to sketch the graphs of these rational functions we're about to look at. Y'all okay? You might need to stand up and stretch. Do the hokey pokey. Help yourself. All right? All right, so let's have a look at example 1. And you have a sheet. Did everybody come in late that didn't get a sheet? Carla, you got your sheet?
The one on my desk?
Yes.
Yes.
Okay. All right, so this is the first example on the sheet, and it's actually a little bit more of a complicated example. So we're going to dive right in with one that has a little bit of everything. All right, so we're going to go back through our notes here and find all the important stuff. So if we're sketching the graph of this function, actually the directions here, let's look at the directions. The directions say to identify points of discontinuities, holes, vertical asymptotes, x-intercepts, horizontal asymptotes, oblique asymptotes, domain of each, and then sketch the graph. So we're going to use all of this information to sketch the graph. All right? So let's dive in. Where do y'all want to start? The order doesn't necessarily matter. If we're sketching the graph, it's always a good idea to find vertical and horizontal asymptotes. So how do we do that? Use factoring, right? Because we're eventually going to want to know the zeros of the numerator. What are the zeros of the numerator going to give us? X-intercepts and or holes, right? And then the denominator zeros give us holes or vertical asymptotes, but certainly values that we need to throw away from the domain come from the values that make the denominator equal to 0. So we're very interested in the values that make numerator and denominator equal to 0. So the factorization of the numerator would be what, Walker?
X squared minus 16x. I mean x squared minus 16.
X times x squared minus 16? Yeah? Factor it.
When you just factor out x?
Yes.
Oh, I forgot. Okay, x times x squared minus 16.
And then x squared minus 16 will factor as x plus 4 times x minus 4. All right. The denominator, let's see, we could factor out a negative 2x, right? And that's going to be x squared plus x minus 2. Right? And then x squared plus x minus 2 will factor as what? X plus 2 times x minus 1 is correct. All right? So based on that factorization, let me come over here. I want to create a box here. And this box is going to have all the information that I'm about to use to sketch the graph. Based on that factorization, what do we know about this function? Somebody just tell me, make some observations. I heard you say something. Enders, what did you say?
I don't really know.
Does this graph have any holes in it?
No.
There's no values that make the numerator and denominator equal to 0? X equals 0, right? Because you see that factor? We see we've got an x in the numerator and denominator, there and there. Right? So there's a hole at x equals 0. Function is broken there. All right, what else do we see from that factorization? Are there any values that make only the denominator equal to 0? What values make the denominator equal to 0? 0, negative 2, and 1. We know that 0 is a hole. What are negative 2 and 1? Vertical asymptotes. Values that only make the denominator 0. X equals negative 2 and x equals 1. Okay? Y'all with me? Let me just ask you some more questions. What is the horizontal asymptote? Do we have one? Y equals 1 over, which is, let's just say y equals -1/2. All right, let's keep on going. What else can we see pretty easily from our factorization there? What are the x-intercepts? 4 and -4. Does it have a y-intercept? How do you find y-intercepts? Plug in for 0 for x. Can we plug in 0 for x? Why not? Because there's a hole at x equals 0. So that hole at x equals 0 tells us that this function has no y-intercept. What's the domain? These are all questions that I could ask you and will ask you on a quiz or final exam. What's the domain of this function? It's everything except for the values that make the denominator 0, right? So what are those values that make the denominator 0? -2, 1, and 0. All right? Now, I know we did this quickly, but everything that we've done here is just straight from the definitions and notes that we just took. How do you find discontinuities? The holes. How do you find holes in vertical asymptotes? They come from what? Values that make the denominator equal to 0. All right? We follow the rules. The degree of the numerator is the same as the degree of the denominator, so the horizontal asymptote is y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. The x-intercepts are the values that only make the numerator equal to 0. That's 4 and -4. Carly?
Is there only horizontal asymptotes if the degrees are the same?
No, if the degree of the denominator is greater, it's y equals 0.
Okay, hold on, wait.
It has a horizontal asymptote if the degrees are the same or the degree of the denominator is bigger than the degree of the numerator. Who had their hand up?
Oh.
Yes.
What was the point of this
Okay, this one there's 3 places where this function has discontinuities. At x equals 0, we have a hole, a removable discontinuity at x equals 0, right? At x equals -2 and x equals +1, we have infinite discontinuities, vertical asymptotes.
Well, wouldn't you know how to distinguish that? In
I probably wouldn't get real specific about vocabulary there. It doesn't hurt to know it, but all right. So let's go back to how do we sketch the graph? The 3 things that we said we would do to sketch the graph is sketch the vertical and horizontal asymptotes, right? Using dotted lines. So we have a dotted line at x equals -2. So, if you guys had colored pencils, this would be a good place to use them if you wanted to. I have the ability to do that here, and so I'm going to make my asymptotes this gold color. X equals 1 is also another vertical asymptote, so I have dotted lines. And what these vertical asymptotes do is kind of divides our graph into 3 regions, right? Y'all see the 3 regions? Okay, I got this region over here, right? I've got, I'll change my color here. Got this region in here, which is white, and you can't see that, right? And then I've got this region over here again. So there's 3 regions that are created by the by the vertical asymptotes. 3 sections, I think we call it in the graph. All right, what is our horizontal asymptote? Y equals negative 1/2 is just a horizontal line right through negative 1/2. So there's y equals negative 1/2. And that takes my 3 regions now and creates like 6 little sections. Y'all see the 6 sections there? All right, what other useful information do we have? Intercepts. -4 and +4, these are actually part of the graph. The asymptotes are not part of the graph. They just tell us where the graph, how the graph behaves. All right, now y'all pay close attention to what I'm about to tell you. Once you have a point in a region, in a section, that's where the graph is in that section. And it has to hug the asymptotes. So this point right here tells me where that graph is in that little section of the graph, and it has to hug the asymptote. So it has to go up here, and it has to go down here. I don't really like what I just did. I think I can make my graph better than that. It's got to hug this asymptote. It's got to come over here and hug this asymptote. Because it's in that region. If I had somehow had a point that was down here, then the graph would be down in that little quadrant, or it's not a quadrant here because there's 6 of these sections. All right? And so I can go over here to the other side and do the same thing. This graph is going to be up here and over here. Really, it's going to go below the x-axis there and stay below it. Get really, really close to 1/2. So it just becomes a question of the center section, right? Where's the graph in that center section? Doesn't cross the x-axis, right? Do we have another x-intercept? Okay, so it's going to either look like this, hug these asymptotes like that, not going to cross the x-axis, or it's going to look like this. How do we determine where it is? You pick a value and plug it in. That's exactly right. And the value we're going to plug in here is x equals, I really only got one x value that's an integer to choose from. What is it? Huh? What'd you say? 3's not in that area. 3's over there to the right. We got to use -1, don't we? We can't choose 0. Can't choose -2. Why can't we choose 0? There's a hole. You actually could choose 0 if you canceled these things out, right? Now the 0's gone. You could put 0 into this, right? But you could take your original function also and just take, we want to find f of -1. F of -1 is -1 cubed minus 16 times -1 over -2 times -1 cubed, running out of time, minus 2 times -1 squared, plus 4 times -1, and y'all can take my word for it because I've already done this. That is 15 over -4. 15 over -4 is down below, right? And because it's down below, my original sketch there is good. Now, just to be really, really technical, I want to show that open circle at 0. There's a hole at 0. We could find that, and tomorrow when we look at this a little bit more closely, we can show where the hole is and get a little better sketch of something like this. But that's what I'm looking for you to be able to do. Yes, ma'am?
Where's the vertex point on that?
We wouldn't have a vertex per se. You could find a maximum or minimum value where that little hump is down below, but you need calculus for that. We wouldn't call it a vertex. We'd call it a local max. Yes?
So we would only do that if there was a third section. So if there's a
Right. If there's only 2 sections, then we're just going to have 2 regions to deal with. Because there's 6 sections. Did y'all understand why it can't be, it has to be up or below? It can't be both, right? Technically, a function can cross a horizontal asymptote. I'm not going to be real ticky about that. But this is a good sketch of what this graph would look like. All right, we'll finish this tomorrow working these examples.